But first, let's turn our attention to how they plan to land the booster. In terms of the timeline, not many anticipate major changes to the process for the booster aside from the landing location. Skipping ahead to the landing procedures, after separating from the ship, the booster will kick off from the boost back engine burn around T plus 2 minutes 55 seconds from the ship to adjust its posture and landing direction. About a minute later, the boost back engine will shut down to transition into the booster transonic phase. At approximately T plus 6 minutes 46 seconds, the booster will initiate the booster landing burn to decelerate and fine-tune its landing position. Once it reaches its designated landing spot, the engine will shut down, marking the successful completion of the mission. That's correct. The basic booster landing procedure will likely remain the same, but adjustments will be necessary to accommodate the Mechazilla arm landing. Let's delve into what those differences might entail. Instead of landing in the Gulf of Mexico, the booster will need to return to Starbase, necessitating additional calculations and considerations. One major concern is fuel. Returning to Starbase will require more fuel for navigation and aligning the landing engine burn to facilitate accurate positioning within the Mechazilla arm. It's crucial to ensure that the booster doesn't run out of fuel during this process, as it could pose significant safety risks. Additionally, the navigation process will be more challenging due to the precision required for landing directly onto the Mechazilla arm. This aspect will demand careful attention to detail during Flight 4's mission. To address these complexities, SpaceX plans to use a virtual tower system to simulate the Mechazilla arm during the landing process. This rehearsal will allow the booster to practice landing steps with a primary focus on deceleration and navigation using the engine and grid fin to achieve a precise landing at the designated location. Indeed, ensuring the Mechazilla arm landing process minimizes any potential damage to the launch systems is crucial for long-term operation. While one flight might not showcase the full extent of potential damage, repeated landings could indeed pose significant risks. To mitigate this, SpaceX could adjust the landing angle to prevent direct impact on the launch systems. By landing at angles that avoid contact with critical infrastructure, such as the chopstick and OLM, potential damage can be minimized. This approach would require careful coordination to ensure the safe capture and placement of the booster. One possible solution is for the chopstick to expand at a position without the OLM beneath it when the booster approaches. Once stable, the chopstick could then rotate to position the booster onto the OLM, thus avoiding damage from the engine's energy flow. Implementing such measures would be essential for facilitating efficient post-flight activities, including repairs, refurbishments, and maintenance works, ensuring the continued reliability of the launch systems for future missions. Indeed, the process of catching the booster is intricate and requires precise control to ensure a soft landing on the chopstick. Smooth speed control is essential to facilitate a gentle touchdown, which may involve a hovering process before the booster is fully captured by the chopstick. This operation adds complexity to the overall procedure. Furthermore, aligning the caught booster to a suitable position relative to the OLM is crucial for subsequent operations. While SpaceX may implement initial alignment measures, additional adjustments may be necessary to ensure proper positioning. This may involve the development of systems on the chopstick to provide slight mobility for the booster, enabling it to move to the required location as needed. These procedures highlight the meticulous planning and execution required for successful booster capture during upcoming flights. Any other important steps or considerations in this process would be vital to address for the safe and efficient operation of the Mechazilla arm system. To tackle these challenges, what upgrades or preparations must SpaceX undertake? As I mentioned earlier, achieving a successful landing demands precision from the engines. However, this poses a significant challenge. Despite improvements, the Raptor engines encountered issues during the initial 3 flights. Particularly in Flight 3, just when success seemed imminent, the engine faltered in the final moments. This disruption thwarted the planned deceleration process, resulting in the premature conclusion of the booster's mission, well before it could touch down on the ocean surface. Ensuring the engine's reliability is paramount for the booster landing mission. SpaceX conducts various tests before flights, including cryogenic, static fire, and wet dress rehearsals. However, true assessment occurs during the actual flight, revealing the engine's efficiency. Flight 4 will serve as a crucial precursor to the Super Heavy booster capture mission. Utilizing a virtual tower during this mission will allow SpaceX to evaluate the engine's performance, facilitating necessary upgrades before implementing the Megazilla arm catch. Additionally, the grid fin requires upgrades as it plays a pivotal role in guiding the booster back to Starbase. The grid fin's performance was a contributing factor to the landing challenges encountered in Flight 3. It must not only address existing issues, but also demonstrate absolute reliability during precision landings, such as those involving the Megazilla arm. Moreover, it needs reinforcement to serve as a reliable attachment point for the chopstick. Given the risk associated with relying solely on the grid fin, SpaceX may opt to install a latch system beneath it for the chopstick to secure to. This approach would minimize the grid fin's workload, reduce repair time, and allow it to focus on its primary functions. SpaceX is upgrading the actuator system for the booster's position adjustment, a crucial component for the upcoming missions. Recently, they replaced the old actuators with new ones and have been conducting extensive testing with this system and the chopstick. These upgrades aim to enhance flexibility in catching the booster or the Starship in the future and facilitate continuous lift up or down processes. Regarding the